All right, this is going on page 82 and we're done. We are looking at semi-log plots again because in 2.9 we looked at them quickly. And I think actually, and this is something, again, my fault, and I never went back and said anything. There was a question on the assignment from 2.9 that expected you to have some information from this lesson that we hadn't done yet. So, but that's okay, we're going to have it now. So in 2.9, we looked at the idea of using a logarithmically scaled axis to help us better understand data that is exponential. We now return to this idea and examine it a little bit more in detail through semi-log plots. Okay. So what a semi-log plot is in a semi-log plot, one of the axes is logarithmically scaled. In AP Pre-Cal, we will only be scaling the vertical or the y-axis. Okay. So while there are different ways to do this, the only way we are looking at it is with the vertical axis being logarithmically scaled. That means our horizontal axis, our input or our x, that's going to be equally spaced like we're used to. Okay. So with a semi-log plot where the y-axis is logarithmically scaled, exponential functions will appear linear. This is basically the big takeaway from this. Okay. Exponential functions appear linear. That's how you're going to be asked a question, something about them being related to each other in some way. If you understand even the bare minimum about what we're doing, you should be able to get that multiple choice question right on the exam. No big deal. Okay? So this is the exact same data that we looked at in 2.9 with the population of English Americans from 1620 to 1820. So here on this first one, this graph on the left, this shows the kind of graph we're used to. Our x values are equally spaced by 20s. Our y-axis is equally spaced by millions. And that's, how we do our scales, right? That's what we're used to. Normal scale. The one on the right is logarithmically scaled. Notice your input or your x-axis, it's still counting by 20s, just like this one is. But your y-axis, first of all, this starts at 1, not at 0. And then it's 1, 10, 100, 1,000, 10,000, 100,000, and so forth. So it is logarithmically scaled. So on the right, semi-log plot, vertical axis has been logarithmically scaled. You should see them with lines on them where we don't actually have a grid on this because the grid would look insane because the numbers are so big. But you would see, something that looked more like this most likely. But before we get there, it says use the features of the semi-log plot above to justify why an exponential model is appropriate for the population. Okay, here's one thing about reading questions, because y'all aren't real good at reading directions, and you have to read questions. I'm totally guilty of that too. You kind of skim it and assume what it's saying. But when we really look at these words, it says use the features of the semi-log plot above to justify why an exponential model is appropriate. It is not asking me if an exponential model is appropriate. So me saying an exponential model is not appropriate doesn't make any sense. This is basically saying an exponential model is appropriate, tell me why. Okay, so that kind of changes your selection of answers. Now, if, let's just say we don't see the axes here, we just see the data, and we were going to go do a regression, would you say that that data looks pretty linear, right? Like I could do a line of best fit that kind of maybe went like that. It's kind of linear-ish, right? And even if I don't feel like it is, that's the connection between a logarithmically scaled graph and an exponential. And it's telling me it is an appropriate model. And I can see that it totally looks exponential when I have it on a normal scale. So then I can say the semi-log plot above appears to be linear. So I didn't say it is linear. I said it appears to be linear, which it does, right? Therefore, an exponential model is appropriate. I think when you're doing statistical type of analysis on things, whether you're in AP stats or some other sort of statistics, then linearizing your data is something that happens. So that's why here, when we actually use the log, it's linearizing this so we can look at our data better, okay? And we're not going to be over-analyzing our linear data. We are just making the connection right now. Very simple. Any questions at this point? Okay. So let's look at this. It says, after Mr. Passwater tells another one of his hilarious math jokes, it begins to spread around the school. The number of people P that have heard the joke after T minutes is graphed on the semi-log plot above, where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P? All right, so when we are looking at this, does that data on that graph appear to be linear? Yes, I would say it totally appears like a really nice line, much nicer than the other one. Since this is a semi-log plot and it appears to be linear, what would be the best model for this? What kind? Exponential, which eliminates A and it eliminates C for sure, right? And then the other two have exponentials in them. There's a couple of different ways to do this. We're going to do this by using our answer choices, and then after we talk about some other stuff, we're going to come back to this one. Then we're actually going to do the math behind it to come up with it, just so that we've seen them both. So what I would do here is I'm going to pick 2 points, okay? And so I'm going to pick this one because this is pretty easy to see. Oh, and I also want to remind you about how we count this, right? So here I start at 1, and then 2, 3, 4, 5, 6, 7, 8, 9, 10. Then 10, 20, 30, 40, 50, 60 to 100, then 100, 200, 300, and so forth. Okay, that's what makes it a logarithmically scaled graph. Looks weird, not how we've ever done it, but they start to get squished as they get to the next level, right? So this ordered pair here, this looks to me like it is at 1, and then I would say, so I start here at 1, 2, 3, 4. Would you agree with 1, 4? So let's substitute that in. Let's find P of 1. P of 1 equals 2 plus 2 to the first, which is 4. Input, output. That one looks pretty good. P of 1 equals 2 times 2 to the first. Well, guess what? That's also 4. Okay? And that happens sometimes. That's why we don't pick the first one we come across and go, ooh, it works. So I need another one. Well, when I look at 2, those lines, especially probably on your paper, are really kind of close together, and maybe I can't really tell exactly where it is. 3, I can't tell exactly where it is because it's in between. 4, kind of same thing. 4 doesn't look like it's right on that line. It looks like it's just a little above it, right? But we're going to kind of just go with that. So if this is my ordered pair here for this point, would be 4, comma, and then this would be 10, 20, 30. So I'm going to put it like about 30. It's 30-ish. It should help me get my answer because I'm not like substituting in 30. So here if I find P of 4, that's going to be 2 plus 2 to the 4th. 2 to the 4th, 2, 4, 8, 16, right? 16 plus 2 is 18. 18 is not about 30, so I don't know that I like that one. Let's see, P of 4. This is going to be 2 times 2 to the 4th. So that's going to be 16 times 2, which is 32. So I think that could look like it was at 32. I mean, it's way closer than this one, so this will be my answer here. Now, if I had a few equations that looked like that and got close to 32, then I'd have to have a different way. That's why we're also going to look at a different way in just a minute. Is everybody okay so far? Questions? All right, flip this over. All right, so an important note here. When we logarithmically scale the vertical axis, we are not changing the actual y values. Okay, the y values stay the same. To logarithmically scale the vertical axis means that equally spaced values on the y-axis are proportional, whereas equally spaced values on the x-axis are linear. Basically saying that your x-axis is like your x-axis has always been, your y-axis gets multiplied instead of, adding so much every time. All right, so here we have, it says the table above gives selected values for the function f. Which of the following graphs could represent these data in a semi-log plot? where the vertical axis is logarithmically scaled. So let's just look at that part first. On A, is my vertical axis logarithmically scaled? No, it's equally spaced like we're used to, right? Can't be my answer. On B, is my y-axis logarithmically scaled? It is, because it starts to get closer and closer, right? So I'm not eliminating B just yet. C, is my y-axis logarithmically scaled? No, so it can't be C. Is it logarithmically scaled on D? Yes, okay. So I got to choose between B and D. So let's just pick a point. Let's pick the first one, 140. We have this ordered pair of 140, right? Let's pick that one. So when I go to 1, is this a 40? No, it absolutely is not. Actually, my y-axis doesn't even go past 10, so that doesn't even make any sense. Let's just double check this one. And this one, I could say that I am at 1, and then 10, 20, 30, 40. That one looks good. D makes a whole lot more sense. Now, I cannot guarantee anything, but if you look at these 4 graphs together, all the questions that I've seen, which, we only have like a year to look at, but when they ask you a question like this, there's only been one graph that looks like this with this type of spacing. Even though this is logarithmically scaled, it's more likely to have multiple ones like this. So chances are pretty good that's your answer. I wouldn't use that just to answer it, but worst case scenario, you can circle it if you had to, okay? Or fill it in or whatever you're doing. All right, next piece of paper, 82. So we're going to practice plotting some of these. I'm going to plot 2 of them with you, and then I want you to try to plot the rest. Remember that your y-axis starts at 1, your x-axis still starts at 0. So I have this ordered pair 0, 200, 0, and then 10, 100, that makes this 200 right there. Okay. Everybody okay with that? Then we go to 125, here's 10, 20. Now, 5 is not right in the middle because you see how it gets closer and closer as it goes up. So 25 really should look more like maybe 0.75. And they're so close together, like you just kind of put it where it's not in the middle. I'm going to have you plot some on your worksheet, but this kind of question would be multiple choice, really where you like have a point and you have to give this. So it'll be easy for you to figure that out. You don't have to worry about getting all perfect. All right, so you try to do C, D, and E. Okay, so remember, if you're pretty darn close to what I have, it should be good. So actually, this one should be pretty exact, but 2, 7. So 2, and then this is 1, 2, 3, 4, 5, 6, 7. A little higher than what I have, but it's hard for me to aim with this. 3.2, 800. So 3.2 is at the little thing here, and then I got 100, 200, 300, 400, 500, 600, 7. Oops. 8 would be like right about there. And then 4.6, 1.5. So this is 1. That would be 2. So 1.5 should be maybe kind of right about there. So when I have you do them, again, try and get them as close to what you think would be correct as possible. But for sure, you need to be able to go the other way. And if you have the points, be able to come up with reasonable answers from a multiple choice question. You're not going to have to write out the numbers. Okay. What questions we got? We good on that? All right. We'll flip it over. All right. As we have seen, if we graph an exponential function on a semi-log plot, the graph will appear linear. In these cases, we can create a linear model for the semi-log plot. Okay, so if I'm given this exponential equation, y equals a times b to the x, the corresponding linear model for the semi-log plot is given by, and it's really log base n of y equals, you can write it different ways, which can be confusing, but I want that log in there for when we talk about this. Now, I want you to look at the equation, one of the equations you already know, which is y equals mx plus, I'm going to put y-intercept instead of b, and I'm going to tell you why in just a second. But that's your slope-intercept form, right? Y equals mx plus b. But notice here we have an a and b in this equation as well, and they're flipped around because they mean something different. That's why I'm just using y-intercept. But this is your slope. This is your y-intercept. It is just y equals mx plus b, basically. But be careful with the b. So it says, note number 1, the slope of our linear function is log base n of b, and the y-intercept is log base n of a. That's what I just said there. The base n corresponds to the base used for the scaling of the vertical axis. Everything we've seen so far is tens. I have a feeling they'll probably use the 10 with you just because they don't want to, it doesn't need to get too crazy. We're just kind of understanding this. Now I'm going to show you, before we do anything else, how we get from here to here, okay? So I have, let's write down y equals a times b to the x power. And we are going to linearize this data. Just like everything else you've done ever algebraically, whatever you do to one side, you do to the other. So I'm going to take the log of both sides. So the log of y equals the log of a times b to the x. Okay, just took the log of both sides. That's it. Just like I could add 5 to both sides. If I wanted to, it's still a balanced equation. All right, so now let's work some log magic. Is it legal to bring the x out in front right now? No, because it only affects the b, right? But can I split this a and b? They're being multiplied, right? So I can split it into two logs that have what? Addition, okay? So that means I'm going to have over here log of y equals log of a plus log of b to the x power. Everybody okay with that? Then I'm going to come up here and say I've got log of y equals log of a plus, now I can bring the x out in front, right? Plus x times the log of b. And that is essentially what we have up there. And I say essentially because this term is written differently and they're flipped around. So if I take this and I make this into log of y equals, so I'm going to take this term and I'm going to make it first because this is my slope and this is my x, right? So log of b times x plus log of a, which is my y-intercept, sorry. But that's where we get that from. This is just plain old log because that's what I choose to do at the beginning, but it could be log base anything. What questions you got? Alrighty, so this right here, this semi-log plot above corresponds to the data for example 3. And example 3 is on the other piece of paper so you can actually see it. It's the table that is where that multiple choice one was. We start with 140, 260, 390. And write an equation for the linear model in this form here. So some ordered pairs that I could get from this, and I'm not guessing, I have the table right here. I don't even have to count this, but I can get these 2 points right here. This one is 140. This one is 260. Okay, I didn't even have to worry about counting the lines because they gave me the data. If I'm going to write the equation of a line, I need a point and I need a slope. I have 2 points, so I can find my slope, right? We know how to find slope. So slope is slope is. And now everything is done with logs here. So the log of 60, minus log of 40 over 2 minus 1. Okay. All right, so 2 minus 1 is just 1. So really I don't even have a fraction anymore, right? Is log of 60 minus log of 40 log of 20? No. What do I do with these when I combine them? Divide. So this becomes the log of 60 over 40. And then again, that would be over 1, so it just kind of goes away. Which means my slope is the log of 3/2. Okay. Any questions at this point? Now, this is going to look weird because it has all these logs in it, but just think lines. It's just lines, and we put the word log in it. It is no big deal. I want to now find the b part. Well, that is my b, but I want to find my y-intercept. So I'm going to use, here, let's just write this down. So log of y equals log of b times x plus log of a. We're going to substitute in what we know. I've got to use one of these 2 points. It does not matter which one. I'm going to pick this one because 1 is smaller than 2 and 40 is smaller than 60, but really it doesn't matter. I can pick either one. So I'm going to take the log of this y value, which is 40, equals, I already found the slope, that's the log of 3/2, times the x value, which is 1, plus the log of a. So if I solve that, I can figure out what the log of a is, right? This times 1 is really just log of 3/2. So I'm going to subtract that over, and I'm going to get log of 40 minus log of 3/2 equals log of a. Everybody with me? We're writing log 1,000 times, but it's still just some basic computations here. Now to combine these two, I make it into division, right? So I'm going to do the log of 40. Now it's divided by 3/2. That means it's times 2/3, right? And that's equal to the log of a. What is 40 times 2/3? This took like 10 minutes last period, and I can stand here all day. Y'all, you are overthinking things. You are trying to make it hard when it is not hard. Trust me. Does 40 divide by 3 evenly? No. So you just multiply it. What do you get? What is 2 times 40? 80. So you get the log of 80 over 3. That's it. That's it. That's all. That's equal to the log of a. Right? Y'all know that. Okay. So now I've got all my stuff, and it tells me to write it in this form. And notice there isn't a log in front of that. That's okay. There's reasons why it's sometimes there and not there. Basically, when you find it, you're finding the log of that number. It is what it is. But so we're going to say y equals the slope, which is the log of b. That is right here, log of 3/2. And I use log base 10 because this is a 10 here. Times x, don't forget your x, plus log of a, which is log of 80 over 3. Okay. Everybody okay so far? Now I want you to look at this and what we just wrote. What is the value of a? 80 over 3. This is the log of a. This is a right here, 80 over 3. What is b? 3/2, right? Just getting it straight from there. Yes, I already did all the hard stuff. I found it. Because this next part says, using the linear model from part A, write the equation of the exponential model right here. Well, guess what? We already have a and b. So y equals A, which is 80 over 3, times B, which is 3 halves, to the x power. That is my exponential equation for that data. What questions do you have? It is an equation of a line. Don't make it harder than it is. Okay? We're going back to page 1. Now, I want you to notice here, I did not have a point at 0, right? So I had to use these two ordered pairs. When we go back to this one, where we already know the answer, we're going to pretend like we don't know the answer. And we're going to pretend like we have other answer choices maybe that are close, and we don't know that this is really it. Okay? And I could start off by using these two ordered pairs that I now know that one's 32, but that's kind of cheating. But I do have this one right here, which I chose not to use this one when we were plugging them in here, because a lot of times when you're testing equations and you use 0 or 1, lots of them work just because of the nature of that number, so it's just not a good number to try. But this is a good ordered pair. That ordered pair is 0, what? 2. Very good. So I can use that. So when I write down my equation, log, and this is a base 10 again, log of y equals log of b times x plus log of a. Yes, I can go find my slope, okay? That's totally fine. But guess what? If my x is 0, do you see how it'll zero out this term? And I have a y, like I'm going to get my answer right away, and then I can go find my slope a different way. So that's what we're going to do here. We're going to substitute in this ordered pair, 0, 2, into here. So this is going to give me the log of 2 equals the log of b times 0 plus the log of a. And because that zeroes out, this zeroes out, I get the log of 2 equals the log of a. So a equals 2. Everybody with me so far? All right, so now I'm just going to rewrite it with the log of 2 there. So I have log of y equals log of b, which I don't know, times x plus the log of 2, because I do know a now. So I have x, y, and b is my unknowns. If I use another ordered pair, this is an ordered pair I know for sure, substitute that in there, then I can find my other unknown. So now the log of the y, so log of 4 equals log of b, which I don't know, times x, which is 1, plus the log of 2. Any questions about where anything's coming from? Just substituting in that ordered pair. All right, so now try to figure out b. So I need to move this log of 2. So I'm going to subtract it. Log of 4 minus log of 2 equals log of b. I have those two logs on the left. That becomes log of 4 over 2 equals log of b. So b is also equal to 2. So then when I have to write my equation, that becomes y equals a, which is 2, times b, which is 2, to the t power. And that's how you get d. Which again, we already know is the answer. We were able to find it a different way, but if they give me certain answer choices and I have to actually do the math, then I can do the math as well. Okay? What questions do you have? Anything?